state the theory on some problem, more or less that we like. They don't have so much workshop. Ah, okay. So, we start with the definition of Weinstein manifold, probably most people know. The Weinstein manifold is the triple W theta F, where W is a 2n dimensional open manifold. Only open means non-compactable without boundary. Theta is a one form on W such that the theta is symplectic. And F is a function from W to R, which is modes, and such that the vector field Z defined by I Z d theta equal theta, that's called the unit vector field, is a pseudo gradient for F. This is not really a low-dimensional talk, but you can make it into one by pretending that n is equal to 2. So, this object, I mean, a function, a Morse function plus a pseudo-gradient induce a handle decomposition of W, which in this case is called the Weinstein handle decomposition. Which has the property that all handles have index at most half the dimension of that. So the index and handles are called critical, and the index the handle of index less than n are called subcritical. So I will make a few examples. There are somewhat two natural sources of Weinstein manifold. The first one is the cotangent factors. The second is smooth affine varieties in CN. And variations of that. And a third observation, you can build them by attaching handles. And the reason is that there is a converse to, so there is somewhat an easy theorem. You have this, you get a handle decomposition where the handles have index less than. There is a less trivial converse that says you have something which has handles up to dimension n, plus some other restrictions which are of a more topical nature in high dimension and more geometric dimension 4, and from that you can construct a Weinstein manifold. So it's something that you have this, more or less these two families that comes very naturally, but also you can construct your favorite ones by an explicit kind of representation.
I mean, is it easy to say how the condition on attaching critical, which critical handles you're allowed to attach compares to, say, building a Stein manifold out of?
It's the same.
It's the same.
Yeah, Stein and Weinstein are equivalent categories. Oh, and there is another source of examples are function surfaces.
So why are there two names?
Because Stein is the original notion in complex geometry. Weinstein manifold were introduced by Weinstein to mimic in the symplectic world what happens for the complex geometry, and it's non-trivial to go from Weinstein to Stein. So I don't think at the time when Weinstein defined them, it was clear that we was defining the same object.
I see. Okay.
But somewhat, it's Stein manifold is a complex surface. It has J which is integrable, and that's it. For example, you don't for doing symplectic geometry, and you cannot keep the J integral. You have to perturb it. So this is the natural notion from a symplectic point of view.
Is Weinstein the same thing as the notion before? Are Stein and Weinstein the same also the notion before?
Yes. So, the remark, we say that W has finite type if F a finite domain critical points. And from now on, I will only consider Weinstein manifold finite type, which, by the way, all the natural examples are of finite type. You probably know, but I will recall what an exact Lagrangian submanifold is. So you have L submanifold of M, which is half-dimensional. There is a principle in topology that interesting things happen in half dimension. Another example. Is exact Lagrangian if the pullback of theta by the inclusion, if the differential of a function h, which goes from L to R, and this function is called the potential of the Lagrangian, of the exact Lagrangian. And we say that L is cylindrical at infinity by the way, I forgot to say something important in the definition, sorry. Otherwise, that doesn't make much sense, everything. So F should be proper. If infinity, if the UV vector field is tangent to L outside the complex. So why is it called cylindrical? Well, you should imagine a manifold like this. So here it is. This is a regular level of F, which is higher than all critical points. And from this on, so you don't have any more critical points, so Z has no zeros. And so you can flow by Z, and you can identify this portion with 1 plus infinity times M with the symplectic form D alpha, where alpha is contact. And a cylindrical at infinity means that your Lagrangian looks something like this. You have some Legendrian in M, and up to here, well, up to some point, it doesn't have to be really here. Up to some point, it's just a cone. In these coordinates, it's just a half interval, half infinite interval times something M, and then it starts again doing whatever it wants here. And just to save time and space, we'll only say cylindrical.
Is it compact Lagrangian cylindrical?
Yes. I mean the end can be empty. So let's make two examples. Compact Lagrangians. And the unstable manifold of the index n critical points of F. So the goal of the talk is to prove that everything that concerns Lagrangian submanifolds in a Weinstein manifold, well, at least everything that can be detected in with Floer homology is somewhat determined by this finite family of cylindrical Lagrangians. Morally speaking, as Yasha said, the reason is, imagine that you are cutting your manifold on these objects. So you should imagine that your manifold is your handles. These are the handles of index n. What is below is subcritical. And you have this object. So you cut along this. So what you do, you are killing all the critical handles. And what remains is subcritical, and by Chilibak, Yasha, and other people, we know that there's not much symplectic geometry in the subcritical manifold. So everything should be contained here. And that's, I couldn't make this argument into proof, even if it's convincing, but it's, some of the proof is dual, but as you will see. I should try to define rough Fukaya categories as quickly as I can. So now the Fukaya category is somewhat a way to package an algebraic way to package the information about the Lagrangians in symplectic manifold.
My mother called me. Great excuse.
And so we want to construct a category whose objects will be Lagrangian submanifolds, and it will be a linear category, so the morphism space will be vector spaces, or modules over some ring, and which will be generated by the intersection of two Lagrangians. Well, of course, we want to have something meaningful. The intersection will be transverse, and so we have to choose some kind of coherent perturbation to make when the Lagrangians are not transverse. But I will somewhat tend to forget about this detail. But anyway, before going back, I have to define Floer homology, which probably many people know, at least in the incarnation here, Floer homology. And so the idea is the following: you have two Lagrangians. I will not be particularly precise about the hypothesis, but they will apply to everything we use here. I want to associate to them some chain complex. So as a group with this will be generated by the intersection points. And for the differential, first we have to fix J in almost construction. Which behaves well in the end, but I'm not, this is a technicality I don't want to go into. And given intersection points, P plus and P minus between the two, I will define a modular space M plus P minus will be the set of maps U from an infinite street R times 0, 1. I will put coordinates as here T there to W such that a bunch of properties are satisfied. US0 belongs to L0, US1 belongs to L1. The limit for S that goes to plus or minus infinity of UST equals to T plus or minus. And finally, they satisfy a Cauchy-Riemann equation. Divide du over ds plus j du over dt equal to 0. Then we want there is an action of R acting in this space because you know, you can take a solution like this, translate by adding something to S, it will still be a solution. And we want that M P minus P plus quotient by this action is a discrete set. Usually it will have several, it might have several components, some may even of different dimensions in the most general case. And so in particular it's not necessarily, I mean that doesn't have to hold for every component, but we throw away everything. I mean not all solutions of this are, that will be isolated, but if they are not, we throw them away, and here we keep only the isolated ones. And then we define the boundaries of P plus and the sum over P minus of the number of points in this modular space P minus P plus quotient by R, which multiplies P minus. It's probably a good idea to do an example. So in blue and red. cylinder, which is the cotangent bundle of S1. Take L0, the zero section, L1, some perturbation of it. This will be our plus, this will be our minus. You see you have two disks. You have a disk like this, and have a disk on the other side. So that means that the boundary of P1 of P plus is equal to P minus by plus, let's say, we work in characteristic 2, otherwise it's complicated, but it can be done. We have two copies of P minus, we have these two disks, so we go to 0. The boundary of P minus is equal to 0 because there is no disk getting out of that, so the homology is generated by these 2 points. More generally,
Are you going to wait by the area?
what?
Don't want to wait by the area?
No, because it's everything is exact.
Oh,
It's important. I mean, I cannot prove the theory for monotone Lagrangians. It's probably still true, but I cannot prove it. And HF of LL, again, because L is exact, otherwise in general it's not true, it is homomorphic to singular homology. So now I rename the boundary as mu1, and I define other operation mu d if you have LD which are mutually transverse. I define LD which goes from CF of LD minus 1 tensor, no, LD minus 1 is D. Dot tensor CF L1 L0 to CF L0 L0. These are defined by counting holomorphic polygons, which means that MID of PD dot U1 is the sum over all P0 of the number of points in the modular space and P0 dot PD times P0. I will give only schematic explanation of what it is. You take a D plus 1 puncture disk, you write it in this funny way. So as a surface with strip-like ends, which D on the right, 1 on the left, and you take holomorphic maps U from this object to W, such that the boundary goes like this. This boundary goes to L0, this goes to L1, dot, 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 the top one goes to LD, and here these three paired lengths ends go to intersection points P0, dot, dot, dot. No, that's not P0, that's P1, dot, PD, and that goes to P6. An example again, which is probably a good idea. Now in three colors, I will do an example of a triangle, and I will let the other you do the other ones. Let's take the two Lagrangians I had before, and then we add maybe a fiber of the cotangent bundle. You see a triangle here. Here you have plus, P minus. You call it this Q1, Q0. Okay, Q1. And since I lost my note, I don't really remember where this triangle goes, but it should be mu2 from Q0 P plus Q0 equal to Q1. Now you enter here and there and there. These operations satisfy the so-called infinite operations relations. Which are an infinite sequence of quadratic relations that are somewhat homotopy, associativity up to homotopy. And I'm not going to write them down because I lost my notes, and I'm surely going to get it. So I'm not ready yet, unfortunately, to define the Fukaya category I want to use, because so far, if you work in a non-compact setting, what I defined is not generally invariant. For example, I can take a fiber on S1, I can move it a little bit, and then it's disjointed, so it's 0, but I also can move it in a different way, and I have a unique intersection point, so for homology is one-dimensional. That's not good. So to have something which is invariant, I have to, well, first let's see why this happens. What happens if I push this away? If I push this away, I have an intersection point that goes to infinity. Which means that if you want to have invariance, we have to have something at infinity that remembers that there was this intersection point. So this is morally the idea, which can be made rigorous, but we prefer not to take anything at infinity. It was all work inside the manifold. To do that, remember that I defined, I said that outside the compact set, W was 1 plus infinity times M D R alpha. So I take a Hamiltonian from W to R that in this region is R squared in compact set, and given L with cylindrical end, I will produce the L rat, which is the image of the time 1 time the 5 time flow of H. So again, what does it do on my favorite example? The cylinder is, this is L wrapped around infinitely many times in both directions. So between L and L rat, for example, we have created infinitely many intersection points. And I define the rat complex as the Floer complex between L0 rat and L1. And the products I've defined on the Floer homology can be defined on rat Floer homology too. You have to be careful that if you have many Lagrangians, you have to wrap them at different speeds. Otherwise, you won't see all the operations that you want to see. Now I can define the Fukaya category of W. This as objects are the Lagrangian submanifold with which are cylindrical and infinity, and the morphisms will be the rough homology chain groups, and there will be the operation that will make an infinity kind. Okay, now you know. So now we can sort of state the theorem, is more or less also the title of the talk. The theorem is, well, it's a joint work with Chantraine Dimitroglou, Rizell, and Golovko. And say that the Fukaya category of the Weinstein manifold finite type is generated by the unstable manifolds of the critical point of F of index n. I should tell now the only thing you don't know is what generated means. So I will give some Mickey Mouse definition of a generation of the Fukaya category. This means for every Lagrangian L and every test Lagrangian T, the rough homology group CWTL is quasi-isomorphic to an iterated cone of, it's time to give names to these objects because it will be important. It's an iterated cone not of D1, Dn, of course, but of CW, T, D1, CW, TDN, but you don't want a random cone. I mean, this will be some vector space if you have plenty of maps between them. You don't want random cones as chain complexes, but you want something that comes from operations, so where the maps are used. By the expression in UK. Rather than giving a more precise definition, I will give at least one example, maybe two. So, what happens if I have two objects and I want to make the cone? That means that, for example, let's say you have D1, D2, and I make the cone over an intersection point. That will mean, I mean, intersection points, you know, it's these are these joints that we are in the rat world, so you have to, that means that CW, and suppose that this is your L. CW TL is quasi-isomorphic to the cone of CW of T D1 in CW of T D2, and here the map that you may put is mu2, where the first entry is taken by P, and the second entry is taken by something here, and it speaks something there. If you have three objects, then you have it. You have three groups, and so the diacritic cone will be will involve different maps and also mu3. So if you have four objects, you will go up to mu4 and so on. Okay, so now we have 20 minutes, which is more than enough to say what I can say about the proof.
Paolo,
Yes.
you always realize the minimal number of generators for the Fukaya category with some function n, or
I have no idea.
in the examples that you looked at?
What?
In the examples that you looked at, or that you know of?
You know, it's hard to make examples. So maybe it's time to mention a few names, even if it's becoming less and less infrequent that you acknowledge other people's work in symplectic geometry talks. Okay, so maybe I shouldn't sign that form now. Okay, well, Fukaya categories were defined, of course, by Fukaya. That's the name gives. Floer homology was defined by Floer. Rank Floer homology was defined by Saïd Abu Zaid. In the exact case, all the perturbations to make all the things were defined by Saïd. And this statement, when proving more or less, was known by everybody. And there is a halfway proof by, I mean, in the general case, there is a halfway proof by Bourgeois, Eliashberg-Ekholm, that were, well, they have a paper that does much more, but it's models some analytical difficulties, and then in particular they can get to apply a generation criterion by Abu Zaid, and that would give that, but again, I say there is analytical work to do. Particular cases, of course, were known, and I'm not an expert on the subject, so I cannot give any comprehensive list of this fact. But the most important case is probably cotangent bundles, which were done by Abu Zaid, and it was probably the original application of this criterion. And many other cases are known, but I'm not particularly. I don't know. I'm kind of quite new at the subject, and making computation is difficult. How the usual generating criterion statement work is you try to you take some set of objects that you think they generate, you compute the morphism between them as much as you can, and then there is some property of the morphisms that tells you that they generate. But you have to understand the morphism in some degree. On the other hand, here as you will see, I will be able to get generation without knowing anything about the morphisms, which from the one hand makes this theorem quite easy to prove in the end if you have the right idea and right technology. On the other hand, you cannot really say that it tells you how the Fukaya category of a Weinstein manifold works, because okay, I give you the generators, but I have absolutely no idea how the morphism should look like. On the other hand, what Bourgeois and Eliashberg did was they tried to understand what the morphism should be, while computing them in terms of some other thing which might be more computable or maybe not. But they are supposed to tell you something about morphisms, and I'm not able to do that.
I'm sorry, so in the case of cotangent bundles, this tells you that the fiber generates?
In the case of cotangent bundle, they say that the fiber generates, yes. And I'd say also in a slightly simpler way than I would say. But then it simply depends what you know. But if you don't know much topology of loop spaces and related things, that's easier. But of course, if you are fluent in that other language, then it might be easy working.
What does the statement do for me?
This statement?
Yeah.
Peace of mind.
Okay.
You know, there is something that should be obvious and you have no idea how to prove it. And then finally you prove it and you realize that it was obvious. And then
Okay. Okay, but then the obvious applications of it.
well, I don't know. Some people are more into Fukaya category, might or might not find some applications.
Okay.
Of course, I mean, what do Fukaya categories do for us? They have been used to prove many interesting theorems. Since they are kind of a new objects also, now computing them just for the sake of computing is something that's considered interesting because it tests our knowledge. And probably in 50 years, we'll not be that much interested in computing them anymore. Like now today, nobody writes a paper, I compute the homology of something.
Mm-hmm.
You know, it's. But in the old days that happened, and somewhat we're in the old days of Fukaya categories. So we can compute very happy.
Okay. Good answer.
So let's say sketch. So the proof is in few number of steps, 3.5 maybe. So first step is 0. We make, well, take L a Lagrangian, and we make L transverse to the stable manifold. Of the critical point. Stable manifold of the critical points of F. So for dimension reasons, this means that L will be disjoint. From the stable manifold of the critical point of index less than n, and it will intersect the other ones infinitely many points. Okay, so let's make a picture. Let's suppose you have two critical points of index n, and we have a man, I will do gender L, maybe something like this. So we have this intersection. At any of those intersection points, we stick a copy of the unstable manifold. So the unstable manifold lives here in the center, but there is a Hamiltonian isotopic copy at any point of this manifold. So we stick a copy here, we stick a copy here, and we stick a copy here. Then there is a concept of Lagrangian surgery, which is more or less what you imagine. You take a double ball where one Lagrangian is Rn and the other one is I times Rn, and you smooth it like this. And you do it at any of these objects, of these points. And we end up with some L prime, which is immersed, and disjoint from the so-called skeleton of W. The skeleton of W is the union of all stable manifolds of the critical. So now we have to prove three things.
Does it matter which resolution you choose?
What?
Does it matter which resolution you choose?
It does. But I was trying to not to. We have to do three things. The first one is for everyone, take a test Lagrangian T, the rough homology of T L prime is defined. So far I've defined Floer homology for embedded Lagrangians. There's a notion of Floer homology for immersed Lagrangians, but unfortunately it's not always defined. So we have to prove that in this case it is. And in general, in fact, it will not if I just stick the things like I have put here. I have to modify it in a good way, and I will show in a picture how to do that. By the way, a remark, I will define what I mean by this, and Janke scolded me that I should not call it Floer homology for immersed Lagrangians because Floer homology for immersed Lagrangians is something more complicated. But I will stubbornly continue to call it Floer homology for immersed Lagrangians. The second thing I have to prove, well, is that CW P L prime is quasi-isomorphic to an iterative cone of CW P the A, well, A are these points A1, blah, 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 A, AN. So the A is a general. Well, let's say the A1, but CW P D AN. And the third point is to show that the homology of H, the wrapped Floer homology of T L prime vanishes. Once I have that, well, I have that. Okay, this is correct. This, and I should put also the L. That is also. So I have a big iterative cones of a bunch of objects that is acyclic. Then simple homological algebra implies that if I single out one object, it will be quite isomorphic to an iterative cone of what is left. And that will, it will end the proof. So I will comment this one first because it's the easy part. Why is this true? So remember the important, we had the property that L prime is disjoint from the skeleton, which means that if we flow L prime by the Liouville flow, we are sent to infinity. And then you see what happens to the generators of T and L prime. Well, you cannot say that they disappear because T might go also to infinity. But the point is, as you flow them up, their action goes quadratically. But then, if you fix an amount of flowing, you can realize it. It's a simple computation by a complex supporting Hamiltonian. And so we will have a continuation map induced by the Hamiltonian that will increase the action by at most something which grows linearly in R. Which means that if you flow long enough, every generator of this every non-zero element in HW blah blah will be mapped by the continuation map to something where there's nothing in the complex. And that means that, well, it could not be zero to start with. So this is the easy part. Now we have these two parts which are the complicated ones, and they're complicated because it's not true what I wrote now, and you have to work to make it true. So let's go again to my favorite example.
If you do the surgery, you don't remain exact, do you? Remain exact?
It depends what you mean by exact. What I have is an immersion I from some L prime to W, and what it remains the case is that I upper star of theta is equal to some H. And the reason is, well, essentially because I'm doing something with something, okay, which does whatever, but the other one are disks, so you can see that you can extend the potential. It's not a problem. However, what you might think is there might be obstructions. Yes, there will be obstructions in general. You will see. So let's take this. The skeleton of the cotangent bundle is the zero section. So that's the skeleton. I take the usual Lagrangian was in all my examples. I stick fibers. Here I have to stick the fibers like this. Why? Well, because how I do the resolution matters. And so I have to put it in this trend way to make the resolution. But now when I do the surgery, you see, when I do the surgery, I create these two, which are called, these two objects which are called teardrops. And teardrops are bad, because if you have teardrops, you cannot define Floer homology. And the reason is, suppose I want to compute the Floer homology between these two things. Now the color code is different from here to there. Okay, you see we have a disk like this, a disk like that, so boundary square is not zero. And why is not zero? Because if I glue the two disks, I have another, I continue the moduli space, I degenerate on the other boundary point, and I degenerate here. So I degenerate to something which is a triangle, to a double points and a teardrop. So teardrops are bad, and you see teardrops here. So how do you adjust the thing? You adjust the thing by sometimes, not always, you can choose a function from the set of the double points to your ground ring which corrects in some one sense the differential. So instead of taking only the usual Floer strip, now you take strip with boundary corner to double points. But then you weight by all these strips by your function, which is called augmentation at the boundary points. And if you're lucky, there are some conditions to be satisfied, you get something which has boundary square equal to 0. So this is well known in the world of contact of contact geometry, because you take an immersed hexagonal Lagrangian, you can lift to a Legendrian submanifold of R times W. The double points will become red chords, which generate the so-called Chekhov-Eliashberg algebra. And what I'm looking for is an augmentation of the Chekhov-Eliashberg algebra. Once I have that, I can define Floer homology, well, either working downstairs or working upstairs as a Legendrian Floer homology, where I put one of the two Lagrangians completely on the top of the other one, so that I don't have, I have chords that only go from 0 to 1, but not from 1 to 0, but not from 0 to 1. And in fact, all the main part of the proof is done in the contact world. So here it's bad, you can see easily that there is no augmentation. So this is not a good situation. You have to change it. And the way to change is, that was more or less inspired by this picture, and then luckily it works in general. You continue flowing in the negative of the red flow until you pass this here, and here you pass this. So you see, now you see this teardrop, but there is also something that cancels. You have to show that this cancels it. But now for this object you can find an augmentation. So this has a well-defined Floer homology. So what's the general lesson that you can learn from this? So more generally, you should partially wrap your disks in the negative direction of the red flow. So this is the negative direction of what you usually wrap when to define rough Floer homology. Until when you do that, the action of intersection points become negative, and it should be negative for well, it decreases, it should be negative for all intersection points except for intersection point near the skeleton. And near the skeleton you have a bunch of intersection points of this type. You have the A intersection point, the one at the skeleton, and you have these other ones, let's call it D and let's call it C, and you always have B and C comes into pair, you have a small triangle with them, between them, and that allows you to set up an inductive process to define the augmentation step by step until you define for everything. And finally, now you have an augmentation, but be careful. The augmentation is not that you define inductively is not on the surgery thing. Is on the object before surgery, which is an immersed Lagrangian, which is a union of a bunch of embedded ones. And now you want to. Then first of all, you stare at the augmentation that you have seen, and you see that by its properties, the Legendrian contact homology of that with any other thing is an iterated cone. So that means essentially that this augmentation respects an order in the lifts of these Lagrangians. And so if some code goes in the wrong order, it goes to zero. The augmentation sends it to 0. So the only holomorphic curves that you're actually counting are those which should be counted in the iterated code. And finally, but now you want an augmentation in the lift of the surgery. So and now here we enter some previous work of Asphalt and Georgios alone, because first thing you can find a cobordism, a Lagrangian cobordism in the symplectization of R times W. So now we have got 2-dimensional above, which has the surgeon manifold at the negative end, and the manifold before surgery at the positive end. And you have an augmentation here at the positive end that you have constructed by the inductive process. The problem with augmentation is that you can pull back augmentation, but you cannot push forward in general. So now we have to use the fact that Georgios has computed part of the holomorphic curves from this cobordism to be able to push forward the augmentation. And so we have an augmentation downstairs, we push it forward upstairs, we push it forward downstairs. And now we want to show that the Floer homology with some test Lagrangian before surgery and after surgery are the same. So we lift that too, and we want to prove that Legendrian contact homology of the lift of the link before surgery and after surgery with this test, with the lift of the test Lagrangian are the same. So now we have, so remember we had a cobordism between these two. We compared, we do the Cthulhu homology with which is something that we defined for cobordism before, with the trivial cobordism defined with this other test guy. Since the surgery is local and the other test guys can be put outside the intersection points, there will be no intersections between the cobordism, and the Cthulhu homology will tell us that the Lagrangian Floer homology on top and on bottom are the same. And that's the end. Sorry for being over 10 by 5 minutes.
Questions?
So if W is the Miller fiber of some singularity, then you know state. So what is the Fukaya, normal Fukaya category of W generated by?
What is the normal?
I mean, look at compound Lagrangians, say.
No idea.
Is it generated by the vanishing cycles or not the vanishing cycles, but
Maybe. I mean, it sounds plausible. On the other hand, if I remember correctly, Helse has an example where you have a torus with a strange local system which is not generated by the vanishing cycles. But if you don't put strange local system, I don't know, it might be. But I'm not really not an expert in that.
But there's nothing like a duality between the wrapped and the unwrapped.
I think there is something like that. I can send you to the paper of Janke where they do something on that direction.
Or is it one?
Yes. I mean, you don't expect to be simple duality. They are infinity objects, and you have to remember the infinite operations. So it has to be complicated.
Okay.
And also, in some sense, if you have a compact object, you can geometrically generate by non-compact ones. I mean, if you follow the construction here, you get what it is the cone, and essentially you do surgery here and there, and you get the zero section plus some jump that goes to infinity. On the other hand, if geometrically, well, it's not much. I mean, there's no way that you put compact things together and get something which has an end at infinity. So it's that it has to be algebraic and complicated if you want to go from the closed one to the non-closed.
Is it easy to say sort of, I mean, what exactly did you do to choose which resolution you took at these intersection points?
It's different. I mean, you put yourself in you choose a Darboux chart where what you see is a product of gadgets like this, and on each coordinate you do this.
Yeah, but I mean, so in that picture, I see no difference between doing that you've drawn and the sort of other resolution of that cross. You know, what's the difference between that and?
Well, that is Well, somewhat that one of the two will give you a cone from the first to the second, and one from the second to the first.
So I could do either one. So there's-
Maybe. And yeah, probably it's some extent it's a matter of ordering.
So like, I mean, say I just, say I started with a 4-ball and attached some, Stein 2 handle to it. I mean, how easy is it to compute the Homs of, the one object that you get here?
Usually it's not easy.
I mean, does the Hom, I mean, do I compute it in terms of like, some sort of contact homology?
Yes, I mean, according to Bourgeois-Liechberg-Ekholm, it should be this isomorphic to the Legendrian DGA of the attaching sphere.
Any more questions? All right, let's thank Paolo again.